Welcome back, students. In this video, we're going to look a little bit into optical activity. Optical activity is a property that we talk about when we start discussing enantiomers because enantiomers are really special. Remember that we said in an earlier video that enantiomers are mirror images of one another, so it's a pair of compounds that are mirror images of one another. And they do not coincide when you put them on top of one another. So they're non-superposable mirror images, and they're a classification of stereoisomers. Because they have the same chemical formula and the same connectivity, and they only differ in the direction that the groups at the chiral centers point, they have the same majority of the same physical properties. They have the same melting point, they have the same boiling point, they have the same solubility. So how the heck do you separate them or distinguish between them? So there's some really cool stuff that happens with enantiomers. One really interesting thing is occasionally some enantiomers will have differences in smells. For example, there's a compound called carvone. One enantiomer of carvone smells like spearmint, which is that mint smell from like gums. And then the other one is caraway seeds. And I don't know if you've ever smelled caraway seeds, but it's very different than spearmint. And it's just so fascinating that they can have a difference in smells or taste. The activity of drugs is probably the most fascinating part of enantiomers, and there's one really terrifying instance of this in history, and that is with a drug called thalidomide. Thalidomide was utilized in the late 50s and the early 60s to treat things like morning sickness for pregnant women. And it was a German drug that was used widely in Europe, and what happened was it actually stayed out of the United States because of a woman named Frances Kelsey. Frances Kelsey worked at the FDA, and she was in charge of a branch at the FDA that did testing for drugs, and she said that there wasn't enough evidence for this drug to be deemed safe, and she was really not treated well because of that. And if you think about the time frame, that makes perfect sense, right? You're a woman in the 60s in charge of a branch at the FDA, and you're withholding a drug and not approving it, you're going to get some flack. And thank goodness that she did, because it gave rise to terrible birth defects. So one of the enantiomers was okay, and the other enantiomer ended up giving rise to really terrifying birth defects, like small limbs. Like the rest of your body is normal size, but your arm is like a quarter of the size that it's supposed to be. It's really very scary and saddening to see the pictures of these babies who experienced the negative impacts of the mom using thalidomide. So we have to be really careful with drugs that have enantiomers because we need to make sure that not just that one of the enantiomers is effective, but that both enantiomers are safe. And then when we think about the inside of body systems, enzymes are like a lock and a key, right? If you don't put in the correct enantiomer, then the enzyme isn't going to do its job. So inside of the body, enantiomers have a big discrepancy on how they behave. Outside of the body, they have the same melting point, they have the same boiling point, they have the same solubility. So how do we know when we have a mixture of enantiomers? This is where the idea of optical activity comes in. If we want to distinguish between a pair of enantiomers, the best way to do that is something called optical activity. Let's talk a little bit about what optical activity is. Now, when we talk about light, remember that light is going to be waves or particles, depending upon which definition you're looking at, that are just going out from any direction from your light source. And that's what this figure is supposed to show. This is randomly oriented light, so light going in all directions. And then what we do is we take a filter that allows only certain directions of that light to go through. And what we get is just one plain polarized light, so light that's going along a certain plane. Why does this matter? Well, our enantiomers will rotate this plain polarized light, and every compound is going to have its own rotation. So these compounds are called optically active because they have the capability of rotating plain polarized light. So we've created the plain polarized light, we hit our sample with the plain polarized light, and our sample will rotate that light. And the direction as well as the magnitude that it rotates is what we take down as the data. If the light is rotated clockwise, we put a plus symbol to that, and we use the symbol of D because this Latin word is too long. And if the light is rotated counterclockwise, then that is considered a negative direction, and we use the abbreviation of L because, again, laboratory is a lot to say. So when we look at an enantiomer or a pair of enantiomers, one of the enantiomers is going to rotate one direction, a certain magnitude. The other enantiomer is going to rotate the opposite direction, but the same magnitude. What if you have a mixture of the two enantiomers? And depending upon what your teacher requires, you might end up going to some really interesting calculations about how you could calculate the percentage of each enantiomer in the mixture. And I'm not going to go into that here, but I do want to talk about something that's really common across all organic chemistry classes, and that's the terminology racemic mixture. A racemic mixture is a 50-50 mixture of a pair of enantiomers. And that 50-50 mixture is not going to rotate plain polarized light at all. This is going to end up with a 0 rotation for that plain polarized light. From this video, I really want you to be able to take away the idea that enantiomers will rotate plain polarized light in different directions, and more specifically, what a racemic mixture is. Because as we start working on chemical reactions in the future, we're going to utilize that term racemic mixture quite often, and we're going to expand upon it as well. We're going to maybe say we created a racemate, or the reaction went through a racemization reaction, which is just saying that there was a racemic mixture that was created at the end. Thanks so much for your attention. This is Katoni signing out.